Okay, today we're going to be talking about normal contact force and motion in a vertical line. So let's consider something on a table. So this is our tabletop, and here, say, we've got a brick. Now, the brick experiences force due to gravity of its mass times the acceleration due to gravity g, and that force is coming down, the gravitational force is pushing down on the brick. Now the brick also has what's called a reaction force. Sometimes known as the normal contact force. So if something's sitting on this table, it's in equilibrium. So when something's sitting on a table or on any surface, there is a force in the opposite direction that is keeping this system in equilibrium. Keeping the system in equilibrium. Now this might seem strange because the force, you don't always think it's the table pushing up on, say, our little brick that we've got on it. But if you think about what Newton says in his laws, that an object is at rest if the forces on it are equal, are in balance. So we know gravity is pushing on this brick, and if there was no force counter to gravity keeping this in equilibrium, the brick would fall right through. This can happen if we had a heavy enough object sitting on our table. Say we had an elephant come and sit on our coffee table and sit down on it. It would be so heavy it would break the table. But in these sort of situations, the weight of the mass of the object is not sufficient enough to do any damage to our surface. So the reaction force is perpendicular to the surface. And it's going to be denoted by a capital R. When the object is on a horizontal surface, the magnitude of the contact force is usually the same as the magnitude of its weight. So when the object is on a horizontal surface, the reaction force is usually equal to mg. And it simply prevents the object falling off or falling through the surface. However, when the surface is tilted, or when other forces act on the object, pushing it into the surface or pulling it away from the surface, the normal contact force is not usually the same as the magnitude as its weight. Now we're going to look at some cases where we move an object that is resting on something else. Now, a situation to think about when you're thinking about the normal contact force, think about in a lift. And think about what you experience. So if the lift is sitting there, stationary, your weight is is pushing you down onto the floor of the lift, and the lift in turn is pushing you up with the normal contact force, the reaction force. But think about what happens when this lift starts to move, or when it starts to go down. Think about how you suddenly feel that kind of, almost like you feel a bit lighter, or sometimes when you feel a bit heavy, like you push down. And this is a result of the different forces that your body is experiencing as the lift accelerates and decelerates, and you're no longer in equilibrium. So we're going to have a wee look at an example. So a crane is lifting a pallet on that rests a stone block. So we're going to have our pallet, and we're going to have our stone block of mass 5 kilograms. The motion is vertically upwards. The crane lifts the pallet from rest at to a speed of not 5, 3 meters per second in 6 meters. Find the normal contact force. So we have force upwards, an acceleration upwards. We have the coming down. We have the 5g newtons of the weight of the block, and perpendicular to the pallet we have the reaction force. So we're going to we need to find out what the acceleration is. So we've got v squared equals u squared plus 2as. So the final speed was 3 squared, the initial speed is 0, and we have 2a times 6. And so that, rearranging all that, we'll get an acceleration of 0.75 meters per second squared. Now, let's think about the forces acting on this block. So F equals ma. So we have the reaction force, which is acting in the same direction as the acceleration. So F, but then the weight's pulling down, so it's going to be minus 5g, and we have the mass, which is 5, times the acceleration, which we know is 0.75. So rearranging all of that, you'll get the reaction force of 53.75 newtons. So with this, it's really important to remember, again, you're remembering what direction things are happening in. So the key to this is the acceleration and the reaction force are both acting in the same direction, and that is opposite to the weight due to gravity pulling down on the block. So if the normal contact force exceeds 650 newtons, the pallet will break, or it's unsafe. Assuming A is the same as we've just calculated, find the limit on the number of blocks. So, to re-diagram, so we've got our acceleration upwards, A. We have our reaction force, and now we have 5. Now each block is 5 kilograms, but we have some number n of them. So let's make n the number of blocks, and that's you'll times that by g, newtons. So it's the same formula, F equals ma, and we still have the reaction force going up minus the weight, and that has to be equal to the mass, which is 5 n's, because the number of blocks times 5, times the acceleration, which we know is 0.75. Now, the reaction force cannot be greater than has to be, let's do it the other way around. The reaction force has to be less than 650. Okay, so we're going to put the reaction force here. So let's rearrange this so that we have five newtons plus 5 times number of blocks, 5 times number of blocks, g times 0.75, and that has to be less than 650. So we'll just rearrange that and use the inequality. Therefore, calculate that all out, we'll have the number of blocks must be less than 12.1. So I hope that helps.